So let's start with the definition. So this is the definition that we learned in the first week. Let's review that again. So linear differential equation is a differential equation of the following form. So you see that each derivative of ith order has degree 1. So the derivative of n order derivative of y has degree 1 in the summation, and also for the other derivative until the y itself, where y itself is considered as 0th order derivative. And you see the coefficients are not just constant, but it's a function of x. So if you have a summation of derivatives with the coefficients as a function of x, then this summation equals to 0 is called a differential equation, a linear differential equation. Now, this 0, if this part, the right-hand side part is 0, then it's called particular homogeneous differential equation. And if this part, in general, we have f of x part in here, and this part is not 0, then we call this non-homogeneous differential equation. So in general, the linear differential equation is of this form, the second equation. Okay, so the second equation is the general form of linear differential equation. And we talked about the uniqueness of solution of linear differential equation with the initial condition that if you have n initial condition for each derivative until n minus 1 order derivative, then the solution is unique. So our purpose is to solve such unique solution, or a general solution which can determine the unique solution. Now, the general method of finding such solution is using the theorem called principles of superposition. So there are 3 principles of superposition. First one is that if you have k solutions, so this is k particular solution. You can have some general solution, but these yi's are considered to be a particular solution because we are going to take a coefficient, the constants, later. So take a particular solutions, and if you take any constant for each particular solution, and if you take the linear sum, so if you take the summation of each function with first degree and coefficients are in constant, then this is called a linear sum. Such linear sum is always a solution of the same differential equation. So differential equation number 3 is this one. Okay, so we are talking about homogeneous differential equation. Okay, so let me state it again. We are talking about a solution of homogeneous differential equation, and if you have any such solutions, the linear combination, linear summation of such solution with some constant is always a solution of, in this case, general solution of the same homogeneous differential equation. So this is the first rule. And the second rule is that if you have a solution to the homogeneous differential equation of the type 3, so here in the equation 3, okay, and let's call it YC. So C stands for the complementary solution. I will explain. We will see why it's called complementary solution later. And let's say YP be a particular solution of non-homogeneous differential equation, as in the equation 4. So when we compare 3 and 4, we assume that these coefficients A1 to A0, An to A0 are the same in 3 and 4. Okay, so we have 2 equations. One is the two equation has exactly same left-hand side. Only difference is on the right-hand side. One is homogeneous and the other is non-homogeneous. And YC is a solution of this the first equation, and YP is the particular equation of the second equation. Then y equals, if we take the summation of YC and YP, then this is a solution of non-homogeneous differential equation in equation 4. Okay. Now this is almost simple because if you take the derivative of the summation of two functions, then you can split your derivative and YC part becomes 0 because YC is a solution of this equation and YP is a solution to this equation. Let me write that in the blackboard. So when you have YC as a solution to non-homogeneous differential equation, and YP as equation of a solution of non-homogeneous differential equation where the coefficients are the same, then if I plug in y equals to yc plus yp into the differential equation, then at each order of y, let's say case order derivative of y is exactly the case order derivative of yc plus case order derivative of yp. So I can simply take ANX yn. So y is now the sum of yc and yp up to a0y equals to an yc n plus yp n up to anx and a0x yc plus yp. Now let's combine all the yc terms. It becomes anx ycn a0x yc, and then let's combine all the yp terms. We have ypn plus a0 yp. So you see the first sum is exactly 0 because this is our assumption. So these part always 0. And what about this part? It is fx because that's our second assumption. So this is equals to f of x. So y satisfies non-homogeneous differential equation. So you might think why we care about some of the complementary solution and particular solution to non-homogeneous differential equation, because you can say that the assumption says we have already a particular solution to non-homogeneous differential equation. Why do we bother to take another form of solution as a solution to the same non-homogeneous differential equation? The reason is this yp is a particular solution. This is not a general solution. This is a single solution. However, yc it could be a general solution. So yc contains a constant, arbitrarily constant in the formula of solution. So when we try to find a general solution to the non-homogeneous differential equation, we have to add a solution containing a arbitrarily constant, which is yc. So the yp, a particular solution we start from, is different from the one that we obtained from this theorem called yc plus yp, in the sense that yp is a particular solution and y here is a general solution. Our purpose, our goal is to find a general solution to a non-homogeneous differential equation, and if the initial conditions are given, then we are going to find a particular solution from this general solution y. Okay? So let's see the third principle. So third principle says that if you have yi as a particular solution to this non-homogeneous differential equation, where the non-homogeneous term is fi for each I, okay, then y defined as the sum of y1 to yk is a particular solution of the differential equation where the non-homogeneous term is sum of fi's. Okay, so why do we care about this third principle? Our goal is to find a solution to this differential equation in below. Okay, we are going to find a particular solution to this differential equation. But if the non-homogeneous term is too complicated, and it's sum of a slightly more simple form of functions, then we were going to split this non-homogeneous term and then try to find a particular solution for each of new differential equation and then combine that into one function to become a particular solution to the original differential equation. So once we do that, we have a particular solution, and we're going to combine with a general solution to homogeneous differential equation with the same left-hand side, and then find a general solution to the non-homogeneous differential equation. So this is a principle. We're going to practice with an example. So let's look at this example. So we have on the left-hand side the linear terms, a linear sum of the derivatives of y, and on the right-hand side we have fairly complicated non-homogeneous term. So we have a polynomial part. This is called let's say call it f1, and we have exponential part. Let's call it f2. Now there's another exponential term, but the difference between this term and this term, can you see it clearly? So the difference between this term and this term is that the exponent has different coefficient. So f2 has exponential to the 2 times of x exponent, and f3 contains the exponential whose coefficient to the exponent is 1. Okay, so there are quite large difference between these two functions. We're going to actually learn why we have to distinguish between these term and this term later. But for now, let's assume that we already split this non-homogeneous term, and we're going to give a complementary solution already. And first complementary solution to this homogeneous differential equation where the non-homogeneous part is 0 is e to the 4x and e to the minus x. So this is the equation. This is a solution to this differential equation. Okay, so this homogeneous differential equation. Note that this left-hand side are equal. And then we also can verify that minus 4x squared is a particular solution to the non-homogeneous differential equation where non-homogeneous term is simply f1, and so for the non-homogeneous term equals to f2 and f3, we have particular solution given as e to the 2x, x times e to the x. So this is a particular solution. You can find another particular solution. We only need to find a particular solution to find a general solution. So this is equation. This is a solution to each of these differential equations. Now, you have to be careful which proposition we are using to propose that this long form of solution is general solution to the given differential equation in equation 5. First, this term, so sum of these yp1 to yp3 is a particular solution to this differential equation 5 because of principle of proposition 3, right? And then this sum of yc1 and yc2 with arbitrary constant c1 and c2 is a general solution to the homogeneous differential equation here because of principle of superposition 1. Okay? And then using the fact that this part, this c1 yc1 plus c2 yc2 is a solution to the non-homogeneous differential equation, and this sum of three functions is a particular solution to the non-homogeneous differential equation. Using the principle of superposition 2, we can say that the sum of these two functions, and these functions, is now a general solution to the non-homogeneous differential equation given in the beginning of the example. Now, the question is, this is a general solution. By definition, if you want to call a solution as a general solution, you can only check that whether there is a arbitrary constant in the formula. So we have C1 as an arbitrary constant and C2 as an arbitrary constant. So this is a general solution. If we want to call this as the general solution, we have to claim that any general solution or any particular solution is derived from this general solution. So there's a difference between a general solution and the general solution. The general solution is the most general solutions. Okay. So our question is, if you found some general solution, how do you check this is the most general solution, i.e. the general solution? So we're going to talk about how to check whether your solution is the most general solution from now on. So we need some of more mathematical terminology. But until now, you have to be comfortable with what we are doing here, because later we're going to learn the technique of finding such particular solutions and the general the YC1, YC2 kind of particular solution, and the YP1, YP2, YP3 types of particular solutions. For now, we have to understand if we are given with the particular solution, how to make a general solution using principles of superposition. So if you have any question, please ask right now. If you don't understand why these are the solutions, I can calculate right here to check whether these are actually the solutions to the given differential equation. So please ask right now if you have any question. Okay, good question. So in the example, how do we split YC and YP? So when you have a differential equation, you always have to find a solution to the homogeneous differential equation, setting this right-hand side equals to 0. That's the YC. And what's YP? YP is a particular solution with the right-hand side survives when right-hand side is not 0. So how we find YC and YP is the topic that we are going to discuss in the next week. For now, YC, let me summarize again. YC is a general solution to the homogeneous differential equation, and YP is a particular solution to the given non-homogeneous differential equation. So another question is, what's the difference between A general solution and D general solution? So let me give an example. Here we have, in fact, this is the general solution to the given differential equation. However, let me write in the blackboard. Suppose that this, let's say y1 is given by c1 e 4x actually minus 4 x squared plus e to the 2x plus x e to the x. This is a general solution because we have arbitrary constant. However, so let me write here. So this is a general solution to the differential equation 5. Is it right? 5. Yes. But, and y1 is derived from more general solution, which is c1 e to the 4x plus c2 e to the minus x plus minus 4 x squared plus e to the 2x plus x e to the x, using by setting c2 is simply 0. So if you want to find a particular solution satisfying a given initial value condition, you have to determine what c1 and c2 is. But before then, before we are given with any condition, we don't know which is become our particular solution. So there are infinitely many solutions, family of solutions. This y1 is a general solution, but this is not really a general form. This is more general. The given y is the most general form of the particular solution, and this covers larger family of solutions. So we cannot say that this is the form that we can derive any particular solution satisfying the initial condition. So there could be an initial condition that is where this function is not satisfied, because we already assume that c2 is 0 in the general form of the solution. So this is called a general solution. So and y is the general solution. We didn't actually claim, we claimed that this is the general solution, but we did not show that this is the general solution yet, because we are going to learn how to check that a given solution is the general solution in short time. So YC is, so YC may or may not be the general solution, because if you're going to find a particular solution satisfying the initial value condition, YC is a particular solution. So it's just the solution that derives from the general solution of the homogeneous part right here. So we have YC as a solution to this given homogeneous differential equation. So this is our complementary solution YC. But if we have initial value IV problem, then YC becomes a particular solution because we are going to find a particular constant C1, C2 satisfying this condition. Okay, so then YC is a particular solution. However, YP, this guy, YP is always a particular solution. Okay? That's why we put P. P stands for particular. Okay, good questions. So we're going to practice lots of examples for once we have sufficient techniques to find such particular solutions. We are just warming up for the next week. So let's move on. So we have definition of linear independency of functions. Let's say we have a set of functions, k functions, f1 to fk, and we say these functions are linearly independent on an interval I. So this is interval I. Okay. If we take a sum of functions with suitable constant and set it equals to 0, implies that C1 and Ck all constant equals to 0. So which means that if we want the sum of functions with constant coefficients to be identically 0, only way we can do that is setting this coefficient as 0. So if coefficients are 0, it's obviously a 0 function, right? We're not talking about that. If we set this equation, if we set non-zero constant C1, one of the constants, at least one of the constants C1 to Ck is 0, non-zero, then we cannot make the sum of these functions to be equals to identically 0. So I will give an example. There's no example. So let me give an example. So easy example is just polynomial. So let's say we have f1 x equals to 1, just constant function 1, and f2 x equals to x. These two functions are linearly independent. Why is linearly independent? Let's say we have c1 f1 plus c2 f2 equals to 0. So this is identically 0. So we're not trying to find a root or solution x satisfying this equation. I'm claiming that if I want to take a constant c1 and c2 such that this sum becomes identically 0 function. So if I plug in this formula, we have c1 plus c2x equals to 0. Identically. And well, let's say when I define a function, I always have to define our interval. So let's say my interval is entire real line, okay? Because this 1 and x are defined entire real line. Now, what I'm claiming is that I want to find C1 and C2 are identically, C1 plus C2x is identically a zero function on this interval R. Can I find any non-zero value C1, C2 satisfying that this equation is true for every R? So every x in R? No. Why? Because if x is 0, then this term disappears. Then C1 equals 0. And let's say x equals 1. Then if I plug in 1 here, C1 plus C2 equals 0. But since I know that C1 is already 0, this means that C2 is 0. So only way I can make the left-hand side equals identically 0 is choosing C1 and C2 equals 0. So this is 0 if and only if C1 and C2 is 0. So conclusion, C1 F1, C2 F2 is 0 if and only if C1, C2 is 0. Therefore, F1, F2 are linearly independent. They're an independent function. Intuitively, what we have here is that if you have two functions, and if you want to claim that these two functions are linearly independent, it means that one function cannot be a constant multiple of the other function. So we have f1 equals to simply 1. So we have one constant function as f1x, and this is y, and this is our f2x. So if you look at the graph of two functions, one function, say you take the f1 function, this constant horizontal line is not a multiple of C2 functions, because if you multiply one function, or graph of one function, then it simply it stretches to the y direction, right? You cannot make some line with a slope by stretching to the horizontal line here, unless you multiply 0, but we're not talking about 0 constants. So here's a remark, summarize. If f1, f2 are linearly independent, abbreviate lin- ind, then the f1 or f2 is not a constant multiple of f2 or f1. So if I start from f1, this is not a constant multiple of f2. If I choose f2, then f2 is not a constant multiple of f1 if f1 and f2 are linearly independent. So this is an example of linear independent functions. Let's give dependent functions, linearly dependent functions. So for example, let's say f1 is x squared and f2 is minus x squared. These two are linearly dependent functions because if I take c1 equals 1 and c2 equals 1, then c1 f1, c2 f2 are simply x squared minus x squared equals 0, identically 0. So I can choose non-zero c1, c2. All of the constant does not have to be 0. We only have at least one constant equals non-zero constant. So if I can choose non-zero constant, either C1 and C2, such that this summation equals identically 0, so F1, F2 are linearly dependent. Okay. So if you reverse our remark here, if you have two dependent functions, then linearly dependent function, then it means that F1 or F2 is a constant multiple of F2 or F1. Okay. So it's easy to check by intuitively by looking at the graph whether these two functions are linearly independent or dependent. Another example of linearly independent function is the exponential function with different exponent coefficient. For example, if you have f1 equals to e to the 2x and f2 equals e to the x, these are linearly independent. Although, if you're looking at the graph, both passes through the point 0, 1, and it only differs by the increasing rate. So this is F1 and this is F2. F1 increases much faster than F2. Now, so it doesn't seem, and well, you can actually see that by multiplying one to one, you cannot make the others. However, if you want to check rigorously why these are linearly independent, you can follow the definition. So suppose that we take fc2 equals to 0, which means that c1 e to the 2x plus c2 e to the x equals to 0. Just plugging any number. So if you have x equals to 0, then it means c1 plus c2 equals to 0. And now, if I plug in x equals to 1, I have a dirty constant here. So let's take a derivative on both sides of this equation, because I want this equation to be equal. This left-hand side equals to 0, regardless of which value of x is. So I'm taking x, I'm taking the interval of these two functions as the real line r. Okay. Now, if I take a derivative, I get 2c1 e to x plus c1 ex, and 0 on the right-hand side. And then let's plug in x equals to 0 to this equation. We have 2c1 plus c2 here. c2 equals to 0. So we have two equations. One is c1 plus c2 equals to 0, and the other is 2c1 plus c2 equals to 0. If you find the solution to these two system of equation, the only solution is c1, c2 equals to 0. So these two functions are linearly independent. Does it make sense? Okay, so let's give another definition. So let's say we have n solutions of homogeneous differential equation of this form. We call this set of solution a fundamental set of solution if they are linearly independent on some interval I. Okay, so this interval is important when we are talking about a solution to the particular solution to the initial value condition. So don't forget about the conditions interval, okay? So we're always talking about the interval. Now, and each I, yi, is called a fundamental solution. So our main goal is to find a fundamental set of solutions, which means that I want to find n number of solutions which are linearly independent on some interval. Okay. So here's the theorem. Let's say we have y1 to yn be a fundamental set of solution to the nth order linear homogeneous differential equation. Be careful that this is homogeneous differential equation. Then the general solution is given by the sum of such fundamental solutions, C1y1 to Cn yn. So also note that there is a D solution, right? It's D solution. So this theorem tells you that how do we check that a given general solution is the general solution. The method is you see the y1 to you see first there are same number of solution to the complementary solution is equals to the order of the differential equation. So check that whether you have n solutions in the general solution, the formula of the general solution, and this n is equal to the highest order term of the differential equation. And then second, check that these solutions y1 to yn are linearly independent so that this becomes fundamental solution. Okay, so here's an example. When you try to find a fundamental solution, you don't try to find a unique fundamental solution. There could be lots of fundamental solutions, lots of set of solutions, okay? So for example, if you have a differential equation y double prime minus y equals to 0, this homogeneous differential equation has a solution which is e to the x, e to the minus x, and also sine hx and cosine hx are all solutions to this differential equation. Now, you can take your fundamental set of solution as set of e to the x and e to the minus x, or set of solution as sine x, as sine hyperbolic sine x and hyperbolic cosine x. So let's see in the blackboard again. So you can take e to the x, e to the minus x, and sine hx, cosine hx. Two sets are both fundamental sets of solution to the given differential equation. Y double prime minus y equals to 0. It's purely up to you which set you choose as a fundamental set of solution. As long as we have a fundamental set of solution, we can write our general solution either let's say y1 as the linear sum of fundamental solutions in this set, which is c1 e to the x plus c2 e to the minus x, or you can take the linear sum of these solutions, c1, well, let's use different coefficient, d1 sine hx plus d2 cosine hx. Now you may ask, you have two different general solutions. Why we call this a D general solution? Because it seems that these solutions seems different, right? When you say the something, it means it's unique, right? If you say a something, a solution, a general solution, it's one of the entire general solution. When I say the general solution, this is the unique general solution. That's the most general solution. These seems similar. This seems different function, but these actually are the same function. Why? Because if I take the definition of hyperbolic sine and hyperbolic cosine, this is nothing but e to the x minus e to the minus x time, plus d2 times e to the x plus e to the minus x. So split this, we have d1 plus d2 over 2 times e to the x, and here we have d2 minus d1 over 2 times e to the minus x. So I can simply take these term as c1 and these term as c2, and there's no difference between the family of solution. If I change my d1, d2 as arbitrarily real numbers, then c1 and c2 in this formula also changes in arbitrarily constant. So basically I get this type of function, right? This type of general solution. So these two general solutions are actually equal. It's the same general solution. So therefore we can say the general solution expressed either in this form or in this form. We can also say, well, this is remark. We can also say combining of these two functions from each set is all fundamental set of solutions. So e to the x and let's say sine x are linearly independent. Solution to y double prime minus y equals to 0, and we have two solutions, right? So therefore it is a fundamental set of solution. I means y equals to c1 ex plus c2 sine hx is also the general solution. Okay, you can express in this way too. Now, here's an important fact. I emphasize that it's important to specify which interval you are talking about. Okay, so can I erase all this? If you have any question, please ask right now before I erase this, because I also want to explain other things. Let me know if you have any question right now. No questions? Okay, so here's the questions. This is mathematical questions. Let's say I have f1x equals to e to the x, and I have f2x equals to so Okay, so here's another example. Let me give another example here. Okay. So I think it's better to. There is an example in the end of the slide. So let me talk about that in the end of the class. So not right now. So after I read on all this, well, I'll talk about that. So so here's another example. We have y double prime minus 3y prime plus 4y equals to 0. And we already know that these two functions, e to the 4x, e to the minus x, are solution to this homogeneous differential equation. So by principle of proposition 1, we can say that the sum of these two functions with arbitrary constant is a general solution, is the general solution. Now, here's another question. So you can check. Let me emphasize before we move on to check this f1, fk. The set of these functions is a fundamental set of solution. You first need to check. So if to the nth order derivative homogeneous differential equation, first you check that there are n number of solutions in the set, okay? And second, f1 to fn are linearly independent, okay? So the question is, how do we know that given set of solutions are linearly independent? So far we are always given the solutions, right? And we know by definition how to check these solutions are linearly dependent by following the definition. Just set the sum of functions and check whether there are non-zero constants satisfying the sum of linear sum equals identically 0. However, that's too complicated. That's complicated, right? So is there any easy way to check whether these two functions are linearly independent without using the definition of linear independency? So here's another definition of stories. So if you have a matrix, the square matrix, n by n square matrix, then the determinant and the entries of the matrix is given as follows. So you have n functions, n differentiable functions. These functions can be differentiable up to n minus first order. Actually, this is a typo. You can have a function differentiable at n minus first order. So this is the n minus 1 function, but that's not important. So the first row is just f1, f2 to fn. And in the consecutive row, you take the derivative of the previous row and up to the nth row, because we started from the 0th order derivative, which is the functions itself. So the last row is n minus 1 order, n minus first order derivative of functions. So we have n by n matrix. We can take a determinant of square matrix. I will explain what is the determinant in the next slide. The determinant is called the Wronskian of functions. And this is denoted by, the determinant is denoted by this W, F1 to Fn, okay? So here's a definition of determinant. If you have a 2 by 2 matrix, suppose that you have two functions, then the Wronskian is given by the determinant of 2 by 2 matrix, and when you take a 2 by 2 matrix, you first take the diagonal part of the determinant and then multiply them together. So take the multiple of AD and take a multiple of the off diagonals BC and then subtract this BC from AD. So this is a determinant of 2 by 2 matrix. And for the 3 by 3 matrix, there are easy way to memorize the formula. There are 6 terms, and 6 terms have either plus sign. So first these 3 factors have plus sign and or negative signs. The term with a plus sign is obtained from this diagonal direction. So when you have AEI, you have 3 factors multiplied together in a different row and different column. You're not choosing an element in the same row or same column. So the way you can choose these 3 elements in this 45-degree angle, this angle is AEI or GBF or DHC. Okay, AEI, GBF, and DHC. So I will explain that in the blackboard in the pictorial way. So and then also when you take the term with the negative is obtained by choosing element in the opposite 45-degree angle. So either GEC, BDI, or AHF. That's how we get the determinant of 3 by 3 matrix. Is there any questions? So here's let me give an example, not in the slide. So how to check the linear independency? For example, let's start from the previous example. We have 2 equations. The Wronskian of these 2 functions is the determinant. So usually we denote by this bar, e to the minus x. And the second row is the derivative of the first row, so ex minus ex. And take a positive and negative here. So in the red line, across the red line, you multiply each entries and take the plus sign. And across the blue line, we take the negative sign. So we have e to the x times minus e to the minus x and minus of e to the x times e to the negative x. So what's the result? So we have minus 1 here and also minus 1, which is minus 2. And this is not equals to 0, not equals to identically 0. So how about the other ones? Let's say we have f1, 1. Let's take 3 functions. f2 equals to x and f3 equals to x squared. Now, the Wronskian of 3 function is the determinant of 3 by 3 matrix. First row is simply the functions itself, and the second row is the derivative of the first row, and the last row is derivative of second row, 0, 0, 2. And when you take the determinant of 3 by 3 matrix, first you multiply across the red line in this direction, and there are 3 ways you can take the multiple of 3 elements in a different row and different column. First one is this one, the other is this one, and the other is this one. So this is obvious, 1, 1, 2. And when I take x to x 0, so I'm going this way, and 0, 0, x squared, we have this way. And For the negative term, so you have this way of choosing 3 elements from different row and different column, and also this way and also this way. So let's take the positive terms. So 1 times 2, and 0 times x times 2x, and here 0 times x squared, and take minus of 0 times 1 times x squared, and here we get 0 times x times 2, and the rest of it is 1 times 2x times 0. So everything disappears, so this is up here. We only have 2. And also 2 is not identically 0. So the reason why I emphasize that this Wronskian is not 0 is that the theorem, this theorem, tells you that if you have n solutions or n functions, it doesn't have to be a solution to the differential equation. Suppose that you have a function, n number of functions. If the Wronskian is not identically 0, then these functions are linearly independent. And conversely, if you have n linearly independent functions, then the Wronskian is never 0. So the previous example that I used in the blackboard is the examples of non-linearly independent functions. So you see these examples again. You see that this is already, we show that linearly independent functions, so the Wronskian is not 0. And these functions are also linearly independent functions. Now, since these are three solutions, we cannot say simply that one function is a multiple of the other, because there are more complicated conditions. However, checking whether these 3 functions are linearly independent using definition is not an easy task, because you have to show that 3 constants are always 0 if it satisfies this given condition of the definition. However, if you just compute the Wronskian of 3 functions with the determinant of 3 by 3 matrix, you can simply show that this Wronskian is not 0, so we can conclude without worry that these 3 functions are linearly independent. Okay. So this is the last one that I want to emphasize, that we said, okay, so here's an example. We have x squared and x times the absolute value of x. So first question is, are these functions linearly independent? The answer is yes. X squared and x times the absolute value of x are linearly independent on the interval entire real line. Okay. However, the Wronskian of these 2 functions are identically 0. Now it seems contradictory, because in the previous theorem that if n number of functions has non-zero Wronskian, then that's the if and only if condition to say that this n number of functions are linearly independent. But here is an example that I will show why this has 0 Wronskian, which are linearly independent, but the Wronskian is 0. If it's linearly independent, intuitively it should have a Wronskian, by the theorem, it should have a Wronskian not equals identically 0. So first, let's check why it has non-zero Wronskian, and also explain why these 2 functions are linearly independent. So f1 equals to x squared and f2 equals to x absolute value x. If you draw these two functions, f1 is simply a parabola f1, and f2 is a parabola, but it's in opposite. It's upside down in the negative side. So it's the same line on the positive side, but on the negative side we have opposite, exactly the symmetric to the x-axis. So this is x, this is y. Now, first, f1, f2 are linearly independent. Let's use the definition of linear independency. If you take c1, f1, c2, f2, then this is c1 x squared, c2 x absolute value of x. And if these are zero identically, so when I say two functions are identically same, I use 3 lines instead of two lines. This is exactly zero. Let's plug in numbers here. So if I plug in 0, then it doesn't tell you anything. So let's plug in x equals to 1. So then c1 plus c2 equals to 0. And what about x equals to negative 1? This means that c1 c1 minus c2. Oh wait, it actually tells you that c1, c2 are both 0. So x equals 2 minus 1. So not the minus 1 here. Oh yeah, that's right. Yeah, that's, it's both 0, right? I'm confused. So when x is minus 1, c1 minus c2 equals to 0. So it means that c1 and c2 are both 0. It should be both 0. So only constant c1, c2 satisfying this sum identically equals to 0 is the 0 constant. So therefore, f1, f2 are linearly independent. Second, let's compute the Wronskian. So the Wronskian of two function is x squared, and let's write our function f2 in two cases. One is x squared and the other x minus x squared. So this is when x is bigger than or equal to 0, and this is when x is less than 0. And on the second line, we're going to take a derivative. So here we have 2x, and here in the two cases we have different derivative. One is 2x and the other is minus 2x. So this is x bigger than or equal to 0, and this is when x is less than 0. So determinant of these two functions are the result is split into two cases. One is when x is bigger than or equal to 0, and the other x is less than 0. So when x is bigger than or equal to 0, this is equals to x squared, 2x, x squared, and 2x. So this is when x is bigger than or equal to 0. And when x is less than 0, this is minus x squared, and this is 2x minus 2x. Right. Less than 0, right? Now, do the same thing just follow the definition of determinant of 2 by 2 matrix. Multiply this direction and then add. Multiply this direction and subtract, and also multiply this direction and subtract this direction. So on the first case, you have 2x cubed minus 2x cubed which is 0. On the second case, you also have minus 2x cubed, and if you multiply these two entries, it's minus 2x cubed, and you take subtraction of minus, so again minus of minus 2x cubed. So these are also 0. This is when x is less than 0. So regardless of the case when x is positive or negative, it always is 0. So this is 0. Now it doesn't make sense because in the previous theorem, it tells you that if it's linearly independent, Wronskian is not 0. What's the problem? The problem is we didn't say the interval. Well, actually, we assume that the interval is entire real line, right? So when we talk about the entire real line as our interval of domain, these two functions are linearly independent. However, when we take the Wronskian of the two functions, we're actually separated the cases when x is positive and x is negative, right? So the contradiction arises because in the first claim, we take R, the entire negative to positive, as the interval of domain, and in the second claim that the Wronskian is 0, we take we separated. We actually separated the interval of domain into two sub-intervals. One is negative and the other is positive. That's why we have contradiction. Well, this contradiction cannot be fixed because in principle, these two functions are linearly dependent. Because if you're looking at the right-hand side of this x-axis, if you're looking at the positive side, the f1, f2 are linearly dependent function because these are just same function, right? Two same functions are obviously linearly dependent. They are the same function. So on the positive side, f1 and f2 are linearly dependent. Okay. How about the other side? So on the negative side, these two functions, now one is x squared and the other is minus x squared, are linearly also dependent. So in this opposite side, f2 is minus x squared because these are also constant multiple to each other. These are linearly dependent. So basically, when we're talking about f1 and f2, if we split our interval into smaller intervals, we're talking about this linearly dependent functions, not independent functions. So the two functions are not fundamentally different. However, when you're talking about the linear independent in the entire real line, you can say that these two functions are linearly independent because on the positive side, these are positively related because f1 times positive 1 is f2. And on the left-hand side, we have two functions negatively related because f1 times minus 1 is f2. So you see that the constant multiple are different on each side. So you can say that these two functions are linearly independent on the entire real line. But when you're talking about the solution to the differential equation, we not always talk about the entire real line as an interval of domain. We only care about the small interval at the initial point. So we want to find the solution curve around the initial point and how the graph of solution look like. So we don't have to consider the entire real line. So suppose that our initial point is on the positive side. So let's say this is our initial point, x0. Then I can only consider our solution curve on the small domain of x0, possibly stretches to the entire positive domain of interval. Then f1, f2 are exactly the same function. So this set of functions f1, f2 is not a fundamental set of solutions. So that's why we have Wronskian equals to 0. So if, for example, if you have a initial point in the negative side, also f1, f2 are not linearly independent. So that's why we have Wronskian equals to 0. So if you want the summary, what's the point? What's the conclusion? Just check the Wronskian, okay? Just check the Wronskian on the small interval around the point, initial point that you want to find your particular solution. If the Wronskian is 0 on that small interval, then two functions or n functions are linearly independent. If it's not, then you're not having a linearly independent solution. You have to find another solution to find the general solution. So this is the end of the lecture today and this week. So next week we are going to actually learn the technique of finding particular solution to complementary solutions and particular solution to non-homogeneous differential equations. And in the rest of the time, we are going to practice the MATLAB, how to find the numerical solution to the given differential equations. So we also, today we also talked about some examples such as these two, right? So these solutions, or which others? Well, also we talked about these solutions. So let's practice the MATLAB. Before we move on, is there any questions? This is the last slide. Okay. Is there any questions? So question is, if the fundamental solution is linearly independent, can we express the general solution in the form of linear, I will take that as a linear combination, okay? So the question is, well, by definition, if you have a some fundamental set of solution, then all the elements in the set are linearly independent. So, okay, so if you have n number of solutions, you take by any means found n solutions to a given differential equation, non-homogeneous differential equation, and if these n solutions are linearly independent, then you can you can say that the set of such solutions are fundamental set of solutions, and the linear sum of such solution is the general solution. Yes. So, as I mentioned in the blackboard, our goal is to find n number of solution if the order of differential equation is n, and check that these n number of solutions are linearly independent. Okay. So here's example that we talked about in the previous lecture. So when we try to solve second order differential equation, you have to split your solution. You have to split your differential equation into system of first order differential equation by setting up new functions. So first, y1 is equals to y and y2 equals to y prime, and now the y is a vector of function consists of y1 and y2, and set up new differential equation in terms of vectors, and y prime, which is given by the matrix containing the derivative of each functions, is now equals to the formula derived from our given differential equation. And then when you plot your result, you have to plot the y1, because y1 is the function of y. The result contains the the value of y1 and y2. y2 is the value of derivative. This is not what we want. We want the actual value of function. So the final result is plotted with the first column of the result of ODE 45. And when you draw ODE 45, let me, for example, give the summarize of what this ODE 45 does. So we need a function which determines the slope of the solution curve and the interval of domain to draw the solution curve and the initial point. This is exactly the same when we talked about the Euler method. So in Euler method, we want to find a numerical solution of this differential equation with initial condition. Now, in the setting, it is hidden, and then also we have y x1 equals to y1. So Euler method is finding these y1. So in order to find y1, the info we need are first the formula of y prime given by this two variable function, and this gives the info on slope, right? Slope of y. And second, we need the initial value x0, comma y0, initial point that the graph passes through in the two-dimensional plane. And third, the interval x1 to x1 interval of domain. So we're going to find a function starting from x0 to x1. So these are three information, and the same type of information are required in the MATLAB using ODE 45. Same type of info is required required in MATLAB to find a numerical solution. Okay? Now, let me give another example here. So we have y double prime. So in the previous slide, what was the questions here? Let's look at this example. So y double prime minus 3y prime plus 4y. Okay. So y double prime minus 3y plus 4y equals to 0. And this example doesn't contain initial value condition. So we have simple initial value condition that y0 equals to 0. And also, let's say I want to find what is y1. So in order to split this into the system of differential equation, let's say y1 is y and y2 is y prime and y1 prime, then y1 and then y prime, sorry. So just take y prime, doesn't matter. And y is y1 and y2. So when you're practice enough, you don't have to put this comment in order to put the command to find the numerical solution. So I'm doing this for your information. And let's see. So y prime is equals to y1 prime, y prime, and y1 prime is nothing but y2, right? But now y2 prime is y double prime, right? y2 prime is y prime of prime. So y double prime is right here given by 3y prime minus 4y. If you put these part to the right hand side, y2 prime is equals to 3y prime. Now, so what is y prime? It's y2, and minus 4y. What is y? It's y1. So I want to express everything in terms of y1 and y2. Now I don't want to express in y or y prime because that's not defined. That's not comprehensible in MATLAB. So this is my f of xy, okay? So y itself is a vector. So let's define xy, f of xy as y2 and 3 times y2 minus 4 times y1. And then solve my numerical solution and by using ODE45. Now the domain, interval domain is 0 to 1 because I want the n value, because I want the value of function at 1. So my end of interval is 1 and start is 0 because I have initial value at 0. So and so this is a second derivative. So we need another info about y prime 0. So let's say y prime 0 equals to 1, okay. Then the initial value has two pieces of information. One is the value of y and the other is y prime. So 0, 0, 1. Okay. So when you use OD45, be careful that the vector f is a column vector. So this y the info about y1 prime and y2 prime is divided by the row using the semicolon. Okay, when I use the semicolon, I change the row. Okay, so this is basically the first row, first column entry, and this is the second row, first column entry. So this f is the vertical vector, and also I have to put the initial value as the column vector, 0 semicolon 1, not colon. Okay, so this is important. So and then let's plot x, y. Now I want plot the value of y, so this is what we want. So it's very steep. Let me erase this x equal. Okay, so this is a result, and if it's not seen here, okay, so now you see that at x equals to 1, it seems like it passes through around 3.25. Now, you don't know exactly the number by looking at the graph. How do you find the exact value? Well, okay, so sometimes if you point your cursor to the graph, then it gives the coordinate of that point, and in this case it just happened to be the point of when x equals to 1, and now y is 3.284. If it doesn't happen, and if you're not too lucky, then you can just simply find your value at the last point by this command. So here's okay, so this command. Okay, so value. So what I'm doing here is by putting this y parenthesis int comma 1 is that when you're looking at the workspace, y here. So wait, okay, so y, you see that the y is now given as 100 times 2 double matrix. And the 100 comes from the fact that I used the interval of domain from 0 to 1 divided into 100 values equally spaced. So y is, this array y is the value of function and its derivative at each x values corresponding to the x array here. So you see, first value of x is 0, right? So this is the x array, the content of x array. First value is 0 and the last value is 1. Okay, I want the value of function at x equals to 1, which means that I have to retrieve the value of array y at the 100th row, at the 100th place. Okay, right here. This is my value of y. What is the value on the second column? This is the value of derivative of y at x equals to 1. So to retrieve the 100th, this 100th is the last entry, so I can simply take the end here. This is useful because I might use the size of array of x as 1,000 or 10,000, but in regardless of the size of x, if I use end here, then I always take the end value, end index of the row in that matrix. So end means I take the end row, and 1 means the first column. So this always works regardless of the size of x. Or if you know the size of x specifically, then just use this 100 column 1 to get the same result. Okay. Now, in the previous lecture, I mentioned how can we take a graph of function around the initial point. So ODE45 only gives a numerical solution from the initial point. Okay, so it doesn't give you the graph before, the shape of a graph before the initial point. It only gives the graph after the initial point. To get the result, I will take another graph. Let's say y1. Let's rename the numerical solution from 0 to 1 as y1. Okay, and draw another one, y2. Sorry, what is y2? y2 equals to result of 45 with the same differential equation, but now I want to go backward. I want to start from 0, but not to the positive direction, but to the negative direction. Okay? So I want to make a line space from 0 to -1. So starting point of the array is 0 and end point is -1. It makes the sequence of array which is decreasing equally from 0 to -1. Okay? So and then I want the same initial value. So initial value is 0, 1. Okay. Now I have two solutions. One is y1, which contains the value of function from 0 to 1, and the other is y2, which contains the value of function from 0 to -1. I want to combine into single plot. So when I do that, I do the same thing, this y2 plot. Now, be careful that when I try to draw two plots in the same figure, I have to keep my first plot and then draw the second plot above that plot, above the first plot. When I do first plot and then do the second plot, the previous plot will be erased. Okay? So I don't want the first plot to be erased. So I should put hold on command so that the plot after hold on will always plot it above this previous plot. And then when I draw all plot that I wanted in the figure, just put the hold off command. So let's look at the result here. So here is sorry. Collapse. Okay. 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 All right. So this is the result. So you see that there are two colors here. The blue one is the graph of solution curve from 0 to 1 of the same differential equation, and the red one is 0 to -1. Simply we take the graph starting from 0 to -1. Okay. So on the 0, 0, we have a smooth connection between two graphs here with the initial value condition. Okay. So if you don't want this separated color, you can give a color option. Let's say I want my first figure be colored in blue. Just put the option single parenthesis, a single quote. Sorry, what is B? Single quote B, and then B stands for blue. And then your graph now looks like one graph. But actually, this is the set of two graphs, one starting from 0 and the other start from 0 to -1. If you want the other color, there are other options. If you put K, and K stands for black, and the graph is now colored in both black. Okay. So it's not hard just to put two graphs, but now you have a graph passing through the 0, 0 with the slope 1, which is exactly the initial condition, initial value condition that we have here. Now you can generalize this method to find a solution to higher order derivatives. Suppose that you have y triple prime plus 2y prime plus minus y prime plus 3 equals to 0. Then I set up three new functions, y1, which is equals to y, y2 equals y prime, y3 equals to y double prime. And using these three functions, I use the vector of functions, y1, y2, and y3. And also this should be column vector. And y prime is now equals to y1 prime, y2 prime, y3 prime. And now it's simple. y1 prime is simply y2. And y2 prime is simply y3. The only difference is y3 prime, which is y triple prime, is now 2 times of y double prime, which is y3, and plus 1 times y prime, which is y2. So let's say 3y here, 3y. And then minus 3 times y1. If you have non-homogeneous differential equation, obviously you can have. So we have, suppose you have sine x, just put the sine x here. So this is the differential equation, a system of differential equation in three functions. So let's see here. Now you can set your function of two variable. Now y is a vector variable as y2, y3, and minus 2 times y3 plus y2 minus 3 times y1 plus sine x. And let's give some initial value conditions. So y0, 0 equals to 0, and y1 equals to 1. So y prime 0 equals to 1, and y double prime 0 equals to -1. Okay. Then xy is solved by ODE 45, f, and lin space from 0 to 1 of initial condition 0, 1, -1. Okay. And let's see the plot. So I'm going to plot the first column because that's the value of y. Here's the, well, this doesn't look great. Let me increase the domain of range, the domain of interval. So let's say we have 5 times pi. Okay, so that's more interesting, right? How about 10 times pi? Okay, well, that's more interesting. It seems like it's oscillating because you have a lot. Can you see clearly? So when you do this, you see the scales are way off different from the scale of x. So there are lots of oscillating here, but eventually decrease. I mean, the amplitude of oscillation is getting larger and larger exponentially. So if you set up your differential equation in different way, then you might see lots of oscillation actually with a constant amplitude. So this can be seen in a spring motion actually. So if you have time, no, we don't have time. So once we learn how to find a solution by hand, we're going to study about the specific case of spring motion or circuit model. So in that case, in that example, we are looking at the complementary solutions and particular solutions and their graphs of solutions. Well, I will explain why the complementary solutions are called complementary at that time. So far, so summarize, we talked about the abstract method of finding a general solution to linear differential equation, and also we talked about the MATLAB, how to use the MATLAB finding numerical solutions. So practice this well, and then there will be a MATLAB homework, and also if we have a midterm online, assuming that we cannot have a actual lecture in the lecture room until the midterm week, we will have some MATLAB problems in the midterm. And also you could have a MATLAB quiz. I mean, the questions on the quiz could be, some of the questions could be MATLAB questions. Okay, so this is it, and thanks for listening. See you on Monday.